Yeah, it's a great pleasure to be here. It was a very stimulating week. It was worth flying halfway across the world just to be here for a few days. And it's especially interesting to be with this crowd and in this session because most of what I'm going to mention has been explained already, so I don't have to re-explain it to you. And I can skip over a lot of technical stuff to focus on results, which is always good. Good. But yeah, I still put a recap slide, which at this point I think everybody here is familiar with in terms of concept. And what I want to focus on today is, well, this sort of standard picture at this point, which is what we believe is the structure of plasma around a typical black hole. The title of the talk is, black hole plasma stuff. But I put an asterisk there because the idea was that what I'm going to say is actually applicable to most compact objects, really. So I want to stay very general. I put this picture here just for reference. And at this point, you all know what we're talking about. We're talking about plasmas in the vicinity of black holes or neutron stars or compact objects, which want to organize themselves in this sort of structure, right? We want to believe that in these situations, we can always sort of identify different regions. There's an accretion disk, which is hot and dense. There's a corona, which is under-dense and very magnetized. And then maybe there's a jet in some situations more strongly than in others. In this context, what I want to focus on is collisionless plasmas and collisionless effects. Because we have plenty of observations that tell us that there's important collisionless, as in kinetic, microscale processes that are potentially affecting both the global scale in terms of structure and observational signatures of these objects. And so black hole with an asterisk plasmas may be likely strongly deviating from the typical assumptions of, let's say, MHD, right? They could be multi-species, multi-temperature, strongly non-thermal, semi-relativistic or ultra-relativistic, depending on the regime. It may emitting radiation, but also interacting with radiation. And so there's a bunch of open questions, which have been already mentioned here a few times, so I'm not going to repeat them. But really what I want to focus on is how do we accurately model this in our simulations. There's many orders of magnitude of difference between the global scales and the microscopic scales. How do we capture that in models in an accurate way? Oh, this is not running somehow. Well, MHD, magnetohydrodynamics efforts, at this point, you are familiar with this, have been running for some time. There's really heroic simulations, including things that are now at the frontier of what is possible. I mean, we just saw a beautiful presentation with these sort of incredibly large simulations that capture the global dynamics very well. Question is, how do we reconcile this with what we know is beyond MHD, right? Because magnetohydrodynamics can be used for global and local simulations, but radiation ultimately is emitted by particles and often non-thermal particles, and MHD doesn't really know about those. And so the classical example of this sort of problem is having a simulation that is processed through some radiation, what we believe is a radiation mechanism that produces radiation maps. And then the problem that the EHT, for example, faces is that you look at these 4 radiation maps, just as an example, you process them through the EHT pipeline to create a synthetic observation. They all match the same observation. So you don't really know which one of these is correct, and you don't really know what exactly to interpret from your observation, right? So how do we go beyond the standard approach? My approach and what I want to focus on is to run kinetic simulations, fully kinetic simulations. And in my particular case, I focus on localized PIG simulations, particle in cell simulations, to tackle specific problems throughout a black hole magnetosphere that then can be hopefully extrapolated to see how this impacts on the global scale. So just to go to the results, I'm not focused too much on what has been said already. Let's start with the disk. Disk is an interesting problem. We just, again, heard a beautiful presentation about some of the dynamics of the disk. What we focus specifically in my group in the last couple of years, and also in collaboration with many of the people here in this room, is the turbulence that happens in the disk. And specifically, if we look at a collisionless disk, where you expect collisionless physics to be important, then the turbulence is collisionless turbulence. And it is a specific type of turbulence which is driven by the magnetorotational instability. So we call it magnetorotational turbulence. And what we want to do with this magnetorotational turbulence is to catch it in the most appropriate regime. This regime is an electron-ion regime. So you have electrons and ions with their realistic mass ratio. Electrons may be relativistic, but the ions may be not relativistic. So we call this semi-relativistic regime. And we want to know, for example, for EHT purposes, we want to know what the electron-ion energy partition is when the turbulent cascades dissipate energy from the large to the small scales. This has been done before, obviously. People have, well, carried out heroic efforts to get such a recipe, really. These efforts are listed here. For example, well, just for example, deciding that this electron-ion energy partition is one number and using it to create those radiation maps that I showed you before, like the EHT does, or with some reduced MHD approaches, non-relativistic gyrokinetics, relativistic collisionless ion-electron reconnection, just assuming a reconnection happens everywhere, and so on. What we wanted to do was to do this properly in the realistic, quote-unquote, type of turbulence that we expect in a black hole disk, which is magnetorotational turbulence. And so this required to really build a big turbulent box with magnetorotational driving and with the conditions that you see here. So the relativistic, semi-relativistic ion-electron plasma with realistic mass ratio. And also we needed to, well, solve some problems with the numerical issues you have when you do this in a shearing box, which is essentially that the initial conditions affect the particle acceleration. If you do all of this, which was carried out last year by Jean, following other works, well then, finally you can see the properties of ions and electrons in this magnetorotational turbulence. And you see, for example, the emergence of beautiful non-thermal tails in both species. But most importantly, what it did last year and finally published this year was this. I consider this to be a beautiful result because it shows you that with our approach, we were able to measure ion versus electron energy partition in a sort of agnostic way. Like you have it, you measure, that is what it is. That is what the EHT should plug into their pipeline if you want. But the interesting bit is that our result, the blue line here, does not match the previous recipes. And so considering those recipes, we believe have assumptions that are not matching realistic accretion disks, then this is interesting because it means that essentially we needed all of this to get to a point where we can really say to the EHT, for example, look, this is the recipe you should be using, not the other ones. So that was a beautiful result, considering the disk, the well, end goal of a number of projects that have been carried out also with people here. And now I want to switch to a different part of the magnetosphere, which is the corona. In the corona, we have super high magnetization. If a corona exists, you can expect these sort of structures, like loops, like in the solar corona, that want to smash into each other and annihilate and liberate a lot of magnetic energy, or you can expect a lot of tangled magnetic field lines decaying into turbulence, which will always result in energized plasma. Focusing on, for example, reconnection, what I did recently in one of my latest solitary efforts, which is probably going to be one of the last ones for the foreseeable future, is to take my code, RelSim, which uses an implicit approach to particle in cell, to conduct simulations with super high magnetization in the ion-electron regime with realistic mass ratio. So this was the biggest simulation really ever done in this regime, and the nice thing if you do the simulation is that you see, once again, you can look at both species, so you can appreciate non-thermal energization of both species for several different sigmas, magnetizations, and you see the emergence of, again, beautiful power laws, but I think the most interesting bit of this work specifically was that when I did this for small and high sigma, I reached a sigma up to 10 here, what I observed was a qualitative change in the behavior of the reconnection physics itself. At small to medium sigma, what I saw was what we expect from 3D reconnection, which is a current sheet that wants to reconnect but also fold and liberate potentially additional energy due to 3D effect. And then when you go to super high sigma, the problem is that it appears like new 3D effects come into play that only are active at super high sigma that effectively quench the ability of your current sheet to deplete itself efficiently, as effectively liberating less magnetic energy than you would expect. I'm very happy to elaborate on this. Unfortunately, I don't have time to go much beyond what I had said. 5 minutes left, perfect. And so I want to highlight just the work of Camille Grenier, who was a postdoc with me. Well, she is a postdoc with me until the next 2 weeks when she's moving to Maryland, who's done a similar work, but in this case, she's looking at the creation of current sheets which don't exist previously, and that appear, for example, at the interface between these loops that are smashing into each other in very high magnetizations. She has looked into this dynamics in 2D and 3D. She has a paper now in the archive. I invite you to look at it. I just want to highlight one final work, also by Jean, from this year, which is concerning turbulence. What he did was taking super high magnetized turbulence in pair plasmas in the corona. And the new bit of information here was to, well, the new approach was to add what we call the leaky box sort of paradigm, in which particles are able to escape from the box. The idea would be that all turbulence simulations are plagued by the fact that heat keeps accumulating forever when you introduce energy. So at some point, our idea was, okay, we want to reach a steady state. Let's let particles flow out when they have, well, according to some criterion. And if you do, then what you observe here is the creation of power spectra that have reached a steady state. So this is the power spectra that we believe, is the correct answer that you should expect in these physical conditions. And the interesting bit is that the particles that are escaping are also carrying away their energy and limiting effectively the energy that you can contain in the system in a certain very specific way. The end result is that beta wants to stay around 1. Again, I'm happy to elaborate on everything I just said. There's no more time in my talk right now. So I just wanted to highlight these results and say that ultimately what I envision is that all these pieces of local simulations placed around a magnetosphere could be put together in a sort of streamlined way, and I believe, strongly believe, this is the way to go. Thank you very much.
Thanks very much, Fabio, for staying on time. John?
Fabio, thanks for the nice talk. I was wondering about the leaky box prescription. When you delete particles from the box, do they have kind of an energy-dependent escape probability? And do you expect this to affect like the steady-state spectrum, things like this?
Obvious question, and always a good question to challenge the approach. The way we did it now was to prescribe not an energy-dependent escape, but a spatially dependent escape, as in they can travel a certain distance from their injection position. The idea would be that there exists a very specific diffusion length, right? And after this length, you can expect the particles to have escaped the accelerator. But that is not the only way to do it. So, for example, these simulations seem to be particularly insensitive of the precise value of the escape distance. But indeed, you could think of having a prescription that's based on energy, and then the question would be, to be answered. We're now doing this for the first time, but I'm very interested in seeing what happens in other contexts.
Hi, nice talk. Have you been tempted to take on the solar corona and make predictions for the last 5 years or so of Parker, hoping he gets it?
Absolutely. Maybe for the people who don't know me, I half of my job actually is on solar physics. So most of what you saw here is really stemming from my high energy inclinations. But I have several students who are actually working on solar physics, and there are students who are working on reconnection in the solar corona with exactly the same approaches. So the answer is yes, and the answer, in development.
But, the global models, I guess, yeah.
Sorry, again?
The global models, yeah. I mean, there's local physics in the solar corona, but also global, trying to.
Oh no! If you're asking whether
wind and things like that, yeah.
If you're asking whether we do global modeling, no, that's, well, I specifically don't. Colleagues of mine do, but maybe I can elaborate. With this.
All right, good, thanks.
I'm a little curious about the accretion slide, like the accretion disk slide when you were having the turbulence, and like I'm not sure if I understand like how does it start. Yes, there. So you have this initial condition and then suddenly goes to turbulence, and I'm not sure what you're showing in there that is happening. Like,
thanks for the question. It's I am aware that this sort of videos are not familiar for people who haven't really worked on this stuff. So basically what you're looking at here is a simulation of a typical simulation, really, of what we call magnetorotational turbulence, which starts from, well, you take a blob of plasma and you put a very weak vertical magnetic field, in there, and then you let the plasma be stirred by a solenoidal forcing, basically the forcing that would be imposed in a differentially rotating disk. Okay, so like you can imagine this is like something that's pulling the plasma in this way, in this sheared way. Okay, and so these magnetic fields get sheared, and the magnetorotational instability kicks in, which takes these magnetic field lines and bends them around, and thereby creating some sort of dynamo action, which exponentially increases the magnetic field you have. Okay, so you're not seeing anything here in the beginning, because effectively the color scale is such that the very weak vertical magnetic field in the beginning looks like it's 0. And then, as the instability develops exponentially, all of a sudden you see some magnetic field there that enters and then decays into turbulence. I think this is Bx, if that tells you anything. One component of the magnetic field.
James?
Does it make more clear, or not really? I can elaborate. Sure, I can elaborate, yeah. Absolutely.
I also have thanks for this nice talk. I also have a question about the shearing box simulations. Are they integrated long enough to get into a steady state?
Absolutely.
Fantastic.
Perfect, beautiful steady state.
And do you get slow-mode dominance in the turbulence?
In what, sorry?
Do you get slow-mode dominance in the turbulence? Like they were showing in this recent MRI Science Advances paper. The slow mode seems to dominate over the alpha modes.
That's a good question. I don't think we looked at it. Our objective was to actually reach a steady state at all, which was not done before. Yeah. But what dominates in the steady state in terms of modes, it's something we haven't looked at.
But you do have energy spectra, as in like turbulent energy spectra for this, and what does it look like?
Well, it's mostly alphanic turbulence on the large scales.
Okay.
So you would believe that there's significant alphanic components. And then what we saw is that there's not much compression, but that may be because effectively the driver is solenoidal. Right? Now, the interesting part of that aspect is what happens at the small scales, because you know all of this from MHD. Effectively, we retrieve MHD results, at least maybe not the one you mentioned, because I'm not sure I'm completely aware about it, but like previous ones that were presented, yes.
Okay, thanks.
I think this is Kawazura.
Yes, this is, I think you have some of their papers, but not the 2024, 2025 Science Advances one.
I missed anything that happened in the last 3 years of my life, so. But I'm curious to know about it. I'll ask you about it. Okay.
So Fabio, if I play the game that my fusion colleagues play on my floor in my university.
You don't have to, right?
Well, I will, just in case. This electron to ion heating ratio, like, what makes you thinking that your peak results are more accurate than gyrokinetics, given that delta B over B at the gyro scale?
Yeah. This is something we discussed
expected
before.
to be orders of magnitude lower than in your simulations?
That's a good question, but I have thought about it in a very limited way. The order 0 answer to myself would be that gyrokinetics does not just assume small armor radii, right? Like, you're assuming that effectively a bunch of things that happen when you don't conserve magnetic moment don't happen. But here, magnetic moment is surely not conserved exactly, and you keep violating the mirror and fire hose thresholds everywhere, so what does that do to you? I mean, I think the ultimate answer is we need a comparison, and I don't think that exists.
And one could do a very elongated big box with as small delta B over B as possible at the gyro scale and compare actually with the gyrokinetic.
Let's find a student to do that.
Okay. Any other questions? All right, if not, let's thank Fabio again.
Thank you.